Hi, this is Miss G. I'm just going to talk about some of the information in section 11.6 and 11.7 and then talk about some of the answers to the problems that you tried in this section. This is a picture here of a molecule and it's held together by covalent bonds. This is a picture of an ionic compound. We're not going to talk about this particular type of compound in this section. These are held together by ionic bonds where you have positive and negative ions that are attracted to each other. This is a picture of a bond, and this is just showing bond polarity. So this would be such where you have two atoms that have differences in electronegativity. That just means that the electrons are not equally shared between the two atoms. Here, the oxygen is drawing the electrons towards itself. It has a greater pull on the electrons, and the carbon is left slightly positive. So this delta negative right here just means the oxygen has a slightly higher electron density around it more of the time, and this delta positive means the carbon is left with a slight positive charge. You can find electronegativity values on the periodic table. Electronegativity is just the ability of an atom to attract an electron in a bond. The electronegativity values are in the top right-hand corner of your periodic table, and you can use this periodic table at any time. So what you're going to see is if you've got electronegativity differences between atoms, if they're different and they're different enough, you're going to have two atoms that make a polar bond. I'm going to put a little table on here that you might want to copy into your notes. We're going to put here bond type, electronegativity difference. I'll just make that the second column, and I'll put an example here. So if you've got a bond type that's nonpolar, it just means that the electrons are shared equally across the bond. There, the electronegativity difference is going to be less than 0.5. So a good example of that would be a carbon-hydrogen bond, because here the electronegativity of hydrogen is 2.1, carbon's 2.5, that difference is 0.4. That's going to be a very small difference, so those electrons will be fairly equally shared. The bond will be polar, meaning the electrons are shared, but they're not shared equally if the electronegativity difference is between about 1.5 and 1.9. So, for example, a carbon-fluorine bond would be an example of that, because there the electronegativity difference is about 1.5. And finally, you have an ionic bond, which we're really not going to talk about too much in this class, and that would be where the electronegativity difference is greater than 1.9. So there, the difference is so great that an electron is actually transferred from one atom to another, making ions that attract. So you might see an ionic bond in something like sodium chloride. So back again to our bond here, carbon has an electronegativity value of 2.5, oxygen has an electronegativity value of 3.5. The difference there is 1, making that a polar covalent bond. So just write polar covalent there. So that's what polar means. Here's a question at the bottom of the page. It said, indicate the polar bonds in each compound. Label the bonds with a delta positive and delta negative. What you're really looking for here is electronegativity differences that are big enough to make the bond polar. So again, the carbon-hydrogen bond is not polar, but the electronegativity difference between carbon and chlorine is such that the chlorine is going to be slightly negative and the carbon is going to be slightly positive. Chlorine slightly negative, chlorine slightly negative. Sorry, that's a negative sign right there. Here again, we have that carbon-oxygen bond. That's going to be polar. The difference is 1.0. Carbon is slightly positive. Oxygen slightly negative. This one has a lot of bonds in it. The carbon-hydrogen bond, again, not polar. Carbon-fluorine, definitely a big enough electronegativity difference. So all the fluorines are going to be slightly negative, leaving the carbon slightly positive that they're bonded to. The carbon-oxygen bond, again, is polar. Oxygen is pulling electrons towards itself, so that makes that slightly negative. The carbon-chlorine bond is also polar. You've got an electronegativity difference there of just 0.5, so that's going to be slightly negative. The fluorine slightly negative, leaving that carbon slightly electropositive. Finally, in D, this benzene ring is just carbons and hydrogen, so we don't have to worry about that. The electronegativity difference is going to be strong enough here around the nitrogen. Nitrogen's got a lone pair. It's got an electronegativity value of 3.0, and hydrogen is 2.1. So that's going to leave this nitrogen slightly electronegative compared to the hydrogen. And there's a difference in electronegativity between the nitrogen and carbon as well. So both carbons are going to be slightly electropositive. And remember that, just for interest's sake, that shape around that nitrogen is trigonal pyramidal. So we're looking at a little pyramid there. This next section talked about the fact that you can have polar bonds in a molecule, but the molecule overall is not polar. Here we've got two dipoles. This just shows that the chlorines are drawing electrons towards themselves. There's a polar bond between the carbon and the chlorine. You can see a dipole going off to the right here, and another equal and opposite dipole going off to the left. But the two chlorines are pulling the electrons from the carbons in equal and opposite directions, so the electrons don't end up going anywhere. So overall, the molecule is actually nonpolar, and the electrons are spread fairly evenly around that molecule. Here's a molecule that is polar, that contains polar bonds. The difference here is the shape of this molecule. You'll see the two dipoles headed towards the oxygen here, which is slightly electronegative up here. Oh, I meant to put a negative sign there. Hydrogen slightly positive, carbon slightly positive. So if you were going to look for a high electron density up here, you would see it around the oxygen, less so around the carbon and the hydrogen. So we can draw a dipole across this molecule, an overall dipole pointing in the direction of where we would find the highest electron density. I like to draw it right on top of the molecule itself. That's a polar molecule. So I'm going to go through some of the answers here. The question was, label each molecule as polar or nonpolar and explain your choice. This is going to be nonpolar. This was an easy one because all of the bonds in here are carbon-hydrogen bonds or carbon-carbon bonds, and they're all nonpolar. Here we have a polar bond, and between the carbon and the oxygen, it's the only one. And because of the shape of this molecule, it's going to be polar overall, and there's going to be a dipole right across the molecule like that. This molecule is a little more challenging because it's not drawn out, but I will draw it out really quickly. It looks like this, and I'm just going to draw dashes for these hydrogens over here. The only polar part of this molecule is right near that nitrogen. The hydrogens are slightly positive, carbon slightly positive, and the nitrogen is slightly negative. And this shape right here is like a little pyramid, and the electrons are more densely found near that nitrogen, so you can kind of imagine near the top of the pyramid is where we see the electrons. So this is going to be a polar bond within here and a polar molecule because of the shape. So that's definitely polar. You might want to draw a dipole right across it towards the nitrogen. The next page was talking a little bit about solubility, and what you needed to know here is that we care about polarity because we really ultimately care about the solubility of organic compounds in different solvents. Molecules like this one are going to be soluble in organic solvents if they contain a lot of carbon in them, if they're organic. So this is going to be soluble in an organic solvent, but it's not going to be soluble in water because this is a nonpolar compound, but water is very polar. And the two do not mix. Don't mix. The water solubility of this is such that acetone is very soluble in water. It's polar and it's small. So you're looking for small and polar, and then it will be water soluble. This molecule here has a polar part, no question, but it's got a huge nonpolar part. It's got way too many carbons in it to be soluble in water. So it's not small. It is slightly polar. So it's going to be insoluble in water. This next section here, you read a little bit about methyl tert butyl ether, PCBs, and DDT. This question is particularly about DDT. The question here was, using solubility principles, explain why shorebirds that populate areas sprayed with DDT are found to have high concentrations of DDT in their tissues. It's because this molecule overall is fairly large, and although it's a little bit polar, especially right here, it's fairly nonpolar overall. So this is going to be soluble in the bird's fatty tissues, and therefore they're going to have a high concentration of this in their tissues. The fatty tissues are organic, and this is an organic molecule, so it's going to be... Here you had to predict the solubility of various vitamins. Vitamin B is going to be soluble in water because it's small and it's polar. It's also going to be soluble in organic solvents, but we're concerned about solubility in water. Here, this molecule is going to be insoluble in water because it's very large, but it's going to be soluble in organic solvents. So one thing to note here is if you take vitamins, megavitamins, and you're taking ones that are soluble in organic solvents or soluble in fatty tissues, they can actually build up to toxic levels in your body, and that can be really dangerous. So I think that ends this section. This was a really quick video on this. If you have any questions, please talk to me as you try the questions that go along with this assignment.
Made with Doodlecast Pro.